I want to finish our discussion on Smith charts by talking about two special terminations, the shorted line and the open line. So for the shorted line, you will remember that if we were to write the load impedance for a short, it's equal to 0 plus J 0 ohms. So the normalized load impedance, lowercase zl, is just going to be 0 plus J 0 ohms. And this corresponds to the far left real line and the J0 circuit. So the point 0 plus J0 is that point right there. So for example, if we were to determine the normalized input impedance of a shorted line with an electrical length of 0.35 lambda, we plot our our normalized load impedance at 0 plus J0, and we would rotate a length of 0.35 lambda clockwise. That would rotate us in this direction, so we rotate a full 0.35 lambda clockwise, and we would then draw our line from here on out, and we would find the intersection of that line with the operating circle, which in this case is that outer perimeter. And we would find out that our new input impedance is 0 minus J 1.38. That's a purely capacitive input reactance. And so we can see that, like we learned already for shorted transmission lines, we can create a purely reactive element with different values just by adding different length of transmission lines. In this case, the 0.35 lambda transmission line length caused us to have a capacitive value. If we had rotated less than a quarter lambda, we would have had an inductive value. We can do similar things with open lines. And for an open line, the load impedance is ZL is equal to infinity plus J0, and that corresponds to the far right of the real line and the J equals 0 circuit or circle. So that is the open on a T-line. So for example, if we were to determine the normalized input impedance of an open T-line with an electrical length of, say, 0.7 lambda, what we would do is we would plot a point at infinity plus J 0, and then we would rotate 0.5 or 0.7 minus 0.5, which is 0.2 lambda. So we would rotate 0.2 lambda. And maybe that doesn't make sense to you guys, so I'll show it graphically real fast. If I was to rotate 0.7 lambda, it would be 0.25 lambda, 0.5 lambda, 0.7 lambda, right? So every 0.5 lambda just gets me back to where I started. So if I'm rotating 0.7 lambda, really I'm just rotating 0.2 lambda. So I start here, I rotate 0.2 lambda, I draw this line, find where it intersects here, and I find that that is equal to Zn is equal to 0 minus J 0.32, which again is a purely capacitive circuit. Like the case of the short circuit, open circuits, Zn can only be a reactive element, and we can make it whatever value of reactance that we like.